Um, yeah, hopefully everybody on Zoom can hear me. So it's a pleasure today to welcome Manuel Pichardo Marcano to give our lunch talk. So Manuel is now a postdoctoral fellow at the American Museum of Natural History, which gives you the best shirts. It's really cool. Before that, he got his PhD last year at Texas Tech. And works on understanding like dwarf binaries and compact objects, and he's going to tell us about those systems today. So over to you, Manuel.
Perfect. So thank you very much. Thank you very much for coming. I'm very happy to be here and talking to you. So please, I'm happy to take any questions in the middle of the talk. It's a very general kind of topic and title that I have, but today I'm going to be talking specifically about two types of accreting white dwarf binaries. And one is the cataclysmic variables, and the other ones are the AM CVns. So this cataclysmic variable is a white dwarf accreting from a main sequence-ish hydrogen-rich star. These have orbital periods of 80 minutes to 10 hours, depending, of course, on the mass of the donor. As the name suggests, and I do like their name a lot, these cataclysmic variables, they're very variable in a lot of different timescales. And one of the most common ones is what I'm going to call what is called dwarf novae, and these are outbursts. They can last days, week. Some of them are normal outbursts. I'm going to call them some of them super outbursts. And what we think they are is this disk instability. And we have this model that we know is not correct, but this is the model we use to try to understand this one. It's called the disk instability model. Has some assumptions that we know is not right, probably like constant mass transfer rate. And there's tons of them. I'm sure a lot of people here work in surveys with supernova. These are your contaminants. There's a lot of these ones, and they find them probably every day, these cataclysmic variables. But what I'm going to be talking about in the second part of my talk is that there's a predicted population in all stellar clusters, in globular clusters. And I'm going to stress this predicted because we haven't found them. And this is the part of the work that I'm going to show you how we're trying to find this and actually place constraints on this binary evolution model on globular clusters, these very different environments than the galactic field. First part of my talk will be about these AM CVns, another type of accreting white dwarf binaries. So you have a white dwarf accreting from another white dwarf, another helium-rich source. These are much compact system, much more. The orbital period can be really extreme, like 5 minutes, and they can go to 70. This boundary is not the sharpest one a minute. So really, really smaller systems, very interesting that hopefully we can try to really simulate this and understand. Again, they're outbursts. They also go into outbursts, and we try to apply kind of the same model and the cataclysmic variable, the disk instability model, but there's much more hope to try to understand these systems because of the scales of this system versus these cataclysmic variables. They're much rarer. They're much less known. There's about 70 of them. There's many more predicted in the galactic field, so there's not that many of them. And this is kind of the picture of the things that I'm going to be talking about. So I work on these systems in the context of two surveys that I perform. And like any astronomer, I'm sorry, they have acronyms. And the order is in the acronym that I like the most. So the first one is TACOS, which is this TESS AM CVn outburst systems. I was using this telescope test to study this outbursting AM CVn system. And that's going to be the first part of my talk. The second one is SCOBAS, which is Survey for Compact Objects and Variables. And this is using another space telescope. In this case, is archival data from the Hubble Space Telescope, looking at variables, compact binaries, and particularly cataclysmic variables in globular clusters. So the first one, the TACOS one, is with TESS. This is a really nice, great mission that I think some people in this institute use for other interesting sources. And it's basically a telescope that is looking at one patch of the sky for a month, 27 days. And it goes to another part of the sky, do the same thing, all for 1 year, and then goes to another part of the sky. So this is great because we have at least a continuous 1 month light curve of interesting objects. This is the first time really there's no night, unless you have a really nice, kind of network of observatory. This you get it for free for a whole patch of the sky with TESS. So at least 27 days, but so if you're lucky enough and one of your sources is in this continuous viewing zone, you get a whole year of observation of these sources. So this is really great and powerful things that we can do with TESS. The cadence have changed. So at the beginning of the mission, you could request for 2-minute cadence data, and the full frame images. Like even if you didn't request the data, it was like half an hour, 30 minutes. But now it's going to be really opening new science because it's going to be 20-second cadence. So imagine that whole month of data with 20-second cadence, and the whole full frame, even if you didn't request the data for a specific object, is going to be 200 seconds. So really, really great, interesting science that we can do with TESS. So reminder, I'm going to be studying with TESS this type of systems. This is what I have kind of in my mind, this white dwarf rotating from another helium-rich star. And I'm going to be talking about specifically ones that have this. So this kind of picture in your head. So I'm going to be talking about these AM CVns, and so I'm going to be talking about a specific range of orbital period for these systems, because depending on the orbital period, you have basically the luminosity, how the mass transfer rate for this system. So below 10 minutes, this crazy system with 5 minutes orbital period, you don't have space for this. So we think we have this direct impact accretors, very interesting sources that I'm not going to be talking about today. Between 10 and 20 minutes, and again, these boundaries is not the perfect boundary. This disk it's all ionized, high mass transfer rate. This is kind of like the nova likes, if you are more familiar with the cataclysmic variables. So we think this is a stable disk. If you go to very long orbital periods, what we think happens is this is a very low state, very cold and stable disk, so it doesn't go into this outburst. So the sweet spot of this outbursting system is between 20 minutes and let's say 40, 60. Again, this boundary keeps changing and increasing, and we have some hints that maybe we have different type of outburst and mechanism that matters more depending on the orbital period. But I'm going to focus between 20 and let's say 60 minutes, where we think we have this disk that you can have this disk instability model, you can have this outburst. And we have at least 2 types of outbursts. For lack of a better name, I'm going to call them normal outbursts, and the other ones are super outbursts. And as you can imagine, the normal outbursts are fainter and last shorter time than the super outbursts. Again, the kind of context how we understand this one is in the disk instability model, where basically you take the disk instability model developed for the cataclysmic variables, and instead of hydrogen, you have this helium, which has a much higher ionization temperature. And we know it's not perfect, and this is the first time we're going to try to really constrain these models if they actually work in AM CVns, because they have some really strong assumptions. To understand the super outburst, the model that we use is called the tidal thermal instability model, and this is telling us that basically whenever the disk grows beyond the 3-1 resonance radius, you create an eccentric precessing disk. So kind of this image to the I guess you're right. And we see some periodic brightness variation that we call super homes, and they are very close to the orbital period. So if you can measure the super homes in this super outburst, then you really have a nice measurement very close to the orbital period. And actually, it's related, we think, to the mass ratio of this system. So it's really powerful if we can measure these super homes. So what we want to do is get better Likers, get really nice Likers of these continuous Likers of these normal outbursts and super outbursts, and really constrain these models in AM CVn systems. Of course, we're not the first one to try to look at these outbursting sources. They were known to be outbursting before, and this is kind of the data we had before. PTF data, of course, CRTS, linear, now CTF is finding many more of these systems, but you see that it's very scarce, and this data, it's not really the best data we can have for these systems, but still there's some relationship people try to find regarding these outbursts. In particular, the first 2 relationships, you have the recurrence time of these super outbursts as a function of the orbital period. And now with TESS, we will try to constrain that to see if it works, how this, with newer data, this relationship holds, and the duration of the super outburst. You see how hard it is if you have these sparse kind of photometric data to really understand the duration of the super outburst. But there's an empirical relationship between the duration of this that is related to the orbital period. So what we want to do, again, is have better Likers to better constrain also this empirical relationship that people have studied in the past with the best available data. But now we have this TESS beautiful data. So finally, I'm going to show you a TESS light curve of one of these systems. This is Assassin 14cc. So in the top is the super outburst, and in the bottom is the normal outburst. So this is test data. Before the super outburst, really these systems are very faint. They can be 20 magnitude, 21 or fainter. So tests do not see them unless they go in the super outburst. So really, most of the time we have nothing, noise. Then they go to 16, 15, 17 magnitude, maybe above the threshold of TESS. So we see the beautiful rapid rise. Then we have this plateau phase in red, and that's what I'm calling the duration of the super outburst, and this very fast decrease. So that is how a super outburst look like. This is for one of the systems. I'm going to show you some other ones. You know, it lasts like, let's say, 9 days, a week, a couple of days. On the bottom, what you're seeing is this normal outburst. And for the first time, we really see the whole shape and evolution of this normal outburst. This is only 1 day, so you can easily see how they can be missed if you don't have a whole campaign to really look at these systems, because they're very short. And one of the first results we got from this survey with TESS is they're actually much more common than previously thought. There were a couple of systems with confirmed normal outbursts, but all of the systems we reported, they show normal outbursts. They seem to be much more common. It's just you really easily miss them. Just one day of duration. So we have the really nice profile of the different type of super outbursts, so we can compare it to cataclysmic variables, because those are the ones that have more model, and try to understand now this system by looking at the different shapes. So this is one type of system as a SIG, and you see that you have the super outbursts and also different types of normal outbursts. And now that we have this continuous, really nice data, we can really try to understand the system. So this is the SAS 14cc, the one that I showed you before. We saw 2 super outbursts, the one I showed you, and now this another one, the second one. And you see before the super outburst, normal outburst, maybe another normal outburst, and then a super outburst lasting about a week or so. This particular source was interesting because it was observed with a really nice ground-based campaign, and there was a bunch of super outbursts of these sources. But the duration we got, it's really different for some of the observation of this source. So is it something within the source? Is it changing the duration of this super outbursts? We really don't know. We just, but that could be a very interesting question. Why the duration, if it's actually really changing the duration? And as we get more test data, we can see if we can get one of those very long 18 days super outbursts, long-lasting period that some people reported in the past. This one was our test one, because we know it's an outbursting one. We also got the orbital period, and it coincides with that. So really nice test data. It works. We see the super outburst. We measure the duration. We confirm the orbital period via the super home variation. So this is one system. Let me show you another one. And you already see it looks different than the other one that I showed you before. And here what I show you is in the top is the CTF light curve, and in the bottom is the TESS light curve. And you see CTF is great that we have it because TESS has huge pixels. Sometimes you don't know what you're looking at. So it's really nice to have some CTF data to confirm you're seeing the super outbursts of this source you think you're seeing. And it's really nice to have TESS data because you really start seeing the details. So definitely this super outburst was caught by CTF, but now with TESS, continuous light curve, you see all the details. And in particular, one thing that I'm trying to highlight here is this precursor. So what happens before this plateau phase, this super outburst phase, that it was missed for this particular source in CTF. And actually, this is the first time that people reported a precursor, this type of normal outburst for the super outburst, and people call it a precursor. They are known to exist in cataclysmic variables, but the first time reported, it was looking at TESS light curve. It was reported by Duffy et al. We did a follow-up survey with many more sources, and out of the 6 sources that we reported for this TESS survey, 5 of them have a precursor. So they seem to be very common. Again, this is no number of statistics, but we will increase the number hopefully by looking at more sources. But they seem to be much more common and just missed. You really needed the cadence and the observation, continuous observation of TESS to see them. So why one of them show precursor versus not? Again, we can go to the models and see what we can learn, press constraints to these models. And so I'm showing you 2 light curves of 2 different systems, where SAS 14cc, the first one you saw with no precursor, and in your left, KL-DRA, the one with normal outburst and precursor. And what I'm showing you in the bottom is some models, how people have tried to explain this in cataclysmic variables. Again, we think that they're more or less related. Instead of hydrogen, one has helium. but this is what we have. We don't have good theoretical models yet with AM CVns, but now we have the light curve to actually go and really constrain this and build nice models that can explain these light curves in AM CVns. And one of the predictions of this model is that if you have a precursor or not depends on the mass ratio. So that's a testable hypothesis. So what we should do is try to measure the mass ratio of these two systems and see if it's indeed this is what it's telling us. Another observation, so what it's the blue line in these graphs on the bottom here shows you when the superhome, this precessing disk, eccentric disk that forms whenever you pass the 3-1 resonance radius. So when the superhome starts also depends on the type of source, because it depends on the where's my mouse? I guess it's here. So here the superhome starts here, versus in this type, the model says that the superhome starts later on the superoutburst. So again, testable hypothesis, when we have higher cadence data, 20-second cadence we will have with TESS, we can actually test and see if these models are working, how people think they are in AM CVns, and actually maybe get some parameters of this system, their mass ratio or something interesting. You might have noticed that you only don't have the precursor and the superoutburst. A lot of things happen after that. And here's 2 light curves of 2 other systems I haven't shown you. And you see already, we only reported 6. There's a whole diversity of morphology of these superoutbursts in this system. So what you're seeing on the top is really noise. This is too faint. Precursor, superoutburst. And what happens after the superoutburst, these are the rebrightenings, or some people call them this echo outbursts. One source in the top, another source in the bottom, the same thing, maybe some normal outbursts before, precursor, super outburst, and then rebrightening, but very different than one in the top than in the bottom. So what we have to do, go to the models and see, work with the modelists and see how you can explain that. The closest thing we had is some models trying to explain this type of echo outbursts seen in cataclysmic variables, and they predict maybe you have a hot and massive white dwarf in the center, can testable hypothesis. Probably hard, but we can measure the hot massive white dwarf in there and see if this is what is actually going there in this type of system in the top. One important thing is one of the modelists, Marie et al. In 2020, they predict that this kind of, to understand, to get this shape of rebrightening, you need a change in the mass transfer rate. You need enhanced mass transfer. So what we're seeing is also for the first time, some sort of maybe evidence that also in this type of systems, at this type of period, you have some enhanced mass transfer that is driving this rebrightening. That's how they try to explain this type of rebrightening in cataclysmic variables. The same in here, and you see different shape of the rebrightening. You have this small one, and then it grows in amplitude and it grows in duration, the second rebrightening, and then the third rebrightening, even more amplitude, bigger direction. And it seems like the system stays actually hot. This is also evidence probably of this enhanced mass transfer in this system at this orbital period. This is what the light curve is telling us if we try to compare it to the models. So this is how they look in CTF. Again, showing you the power of CTF to really confirm this. It was shown here, and really the details that you see in TESS. The other thing that is nice to have other data, TESS just looks at one band, very kind of reddish band, because it's really just exoplanet hunter, but of course we're using it for something else. But CTF has colors, and we have the details. So what we can do now is look at the color evolution of this type of system, and how is the color evolution of the superoutbursts and rebrightening, and of course compare to the models and see what kind of mechanism is driving this type of superoutbursts. This is very sparse data. What we really want is something like in the bottom with a lot of data. But again, so Liliana Rivera Sandoval et al. She showed that the color evolution tells us something interesting. So we should be studying the color evolution of this type of superoutbursts. So this is what I'm showing you is R and then G minus R, and they is from the maximums, from the superoutbursts. And it's a bit of a mess, especially in the rebrightening. But the shape that we're looking at, it's really that as it gets brighter, it gets redder. And this is more or less what we see in cataclysmic variables with this disk instability model, the prediction from this disk instability model. This is different from what we see from another type of AM CVn with much longer orbital period. And the shape, again, much more better data, but this is telling us that we should be looking at color evolution of these outbursts, is instead of getting redder, as you get brighter, you get bluer. So this is a different behavior that we see in the long orbital period system. This is a period with 60-minute orbital period, reported by Liliana Sandoval et al., versus this kind of shorter orbital period. And what they claim in this paper is that this is some evidence, again, of Higgs mass transfer and different mechanism driving the super outbursts at different orbital periods. So we did that for this source, and then beautiful CTF light curve, beautiful TESS light curve, color evolution. Same kind of big pattern of as they get brighter, gets this redder. What you predict, that is when the driver, the physical mechanism is this instability model in this kind of systems. Again, the rebrightening, I don't know what to say about that. This is really a mess, and we really need nicer data in this type of shorter orbital periods and compare it to what we know of AM CVns and cataclysmic variables. That data point, I have no idea. So don't ask me about that. Nice. So I'm going to show you a few more light curves. So this is Gaia 16.0. It's an interesting one because we were lucky in the sense of we got one whole year of data. So imagine that you have 2-minute cadence. Sometimes we have 30-minute cadence, but at least in some sectors, 2-minute cadence for a whole year. So we were really able to constrain the recurrence time of this super outburst. So we did that for this one, and this is a bunch of for the first part of this survey, all of the type of super outbursts that we saw. We also saw normal outbursts, again, very common, and it's interesting to see the recurrence time also of these normal outbursts and if they happen in all kind of systems and how often they happen in different type of systems. But for this one, observe basically a year. We measure very precisely in the sense the recurrence time that we were able to continuously see the light curve of 203 days. TESS is great because we have 2-minute cadence. We will have 20-second cadence. Remember those super homes. We measure the super homes. It's very close to the orbital period, and we got the orbital period for this system. So this is also one power of TESS. If you see the super outburst, you should be able to measure the super home variation. So you should be able to measure the orbital system, the orbital period, because it's very hard to do this because some of these are very faint, and you really need, and their orbital periods are very, very short. So with TESS, you get them basically for free. So we can start building also this orbital period, recurrence time, for example, data set, and really constrain this empirical relationship. Yeah, we saw those normal outbursts. Of course, I'm not going to talk in detail about this one, but we saw other type of behavior. This was for the first time we looked at this test, and we saw all kind of systems with all kind of different behaviors. So there's really interesting morphology depending on the type of system. So this has some sort of cycle that we don't really understand, but it's going to be interesting to look at it with more and getting more TESS light curve and maybe even targeted photometry for these systems. And something also very interesting is it seems like not only you can measure the orbital periods of the system during a super outburst, but also during the normal outburst. And this is predictable. We should measure the orbital period of the system, but we got a periodicity in the light curve of the normal outburst of 25.7 minutes, which is kind of a reasonable orbital period, and it agrees with the empirical relationship of their recurrence time. So what are we seeing? Are we actually seeing the orbital period? Can we get the orbital period just by looking at the normal outburst? That would be great to really confirm among all those CVs candidates, because everything is a CV until otherwise it's not. If we can really get those periodicity just from looking at the TESS light curves, if we have the cadence. So why is it a permanent super humper that we always see the orbital period? There's some of them in the cataclysmic variable world, and you see that it depends on the orbital period and depends on the mass transfer rate. So is this what we're seeing or not? It will be interesting to confirm it and to see if we have more of this system. So even the normal outburst can tell us something interesting. So to start wrapping up, the first result, big result we got is that we measured the super outburst duration of all of the systems that we saw in TESS in our first part of the survey. We have the orbital period. For some of them, we got the orbital period for the first time, and really doesn't agree with the other recurrence time. So what we're thinking is this was done with the best available data at the time, which was some surveys from the ground, and you really see how easily you can, or how hard you cannot separate the super outburst from the rebrightening. So that's what we think we're seeing here. That TESS, you really see the super outburst, then the rebrightening with CTF. you see Hall, and it's really hard to measure precisely the super outburst duration. So to conclude, first part of my talk with tacos is we saw a lot of super outbursts, we saw a lot of normal outbursts. They're much more common than previously thought. They are very easy to find. You saw it's only one day. We finally got the shape. We finally have statistics. We're building the statistics of which systems and how often these normal outbursts occur. The echo outbursts, there's a whole family of them, different morphology. We saw evidence by looking at the models that also enhancement transfer is probably necessary to explain this behavior of these systems. So, and more work should be done here. Those super outburst duration were overestimated. So we are refining those empirical relationships they found, and we found probably that it probably doesn't matter, but this is a short orbital period range. We should expand it and see how well behaved this, if there is a relationship. We find two new orbital periods, from the super homes and even from the normal outburst, maybe a permanent super home pair. And color evolution is important. We should be looking at color evolution of these type of systems and the super outbursts in these systems and compare it across the orbital period and compare it and try to see and compare it to what models predict and see what physical mechanism is driving these sort of outbursts. And it's probably both, probably some disk instability model, probably some enhancement transfer too. So now I'm going to change into another type. So if you have any question, of course, feel free to interrupt me if you have any question regarding the AM CVns. Now I'm going to the second survey, which is the survey for compact object variables. And this is the focus of this. It's going to be cataclysmic variables. So this is kind of the picture I have in my head. This is a main sequence hydrogen-rich star. That's the donor being accreted by a white dwarf. So yeah, via Roslow overflow, they tend to have a disk. If they're not magnetic, depending on the magnetism. So you have, I will show you some example of how a magnetic CV could look like. And they're very variable, especially this Dwarf nova, this normal outburst, this instability in the disk. It's very common. That is the most common type of cataclysmic variables. And you can increase by 2.8 magnitudes during those normal outbursts. Different type of family of CVs. Again, this what I'm going to call Dwarf novae disk CVs, that you have this disk instability. You have these magnetic CVs, and depending, you have intermediate polars that you have truncated disk, or when the magnetic field is too strong, you have these polars, and the accretion is directly from the magnetic field lines. So we know a lot about field CVs. This is a color magnitude diagram of where the cataclysmic variables. This is in Gaia data, and of course, between the white dwarf sequence and the main sequence. So I'm showing you this to see, we know a lot of them, we know the distance, we have a nice picture, more or less, of these field CVs, and some of them are in Gaia. And the color is the orbital period. And what I want to stress here is that the orbital period tells you something about the donor, because it's Roslow field and tells you something about the history of this cataclysmic variable, if it formed from normal binary evolution of nothing weird happening. You have a binary and then you form a CV. So the orbital period traces this evolution. So you have these old CVs close to the white dwarf, this period bouncer, we call them, and this young, bigger donor with orbital periods, larger orbital periods close to this main sequence. We have a picture, we have a bunch of orbital periods of the system. So we have a period distribution with and a period gap. So there's a shape, so we can try to explain this depending on the mechanism that is driving the angular momentum transfer, or taking angular momentum from the system. So really nice period distribution of these systems, and the period tells you something about the evolution of these cataclysmic variables. We have a nice sample, so we can have a population and tell which one is the most common CV. And in the field, the most common CV is this Dwarf novae, that go into outbursts, this transient, these outbursting sources, 60%. Some of them magnetic, of course, and then some of them are these persistently bright nova-like CVs. And that's why we see them. I mean, there's a lot of them. Like maybe you don't see it here, but it goes into outbursts. We picked it up with our nice surveys that we have from the ground, and there's a lot of them. So there's, of course, CRTS, and they're all wonderful. ZTF now, there's going to be even more with the Vera Rubin LSST. Even Gaia is a transient detector. I mean, and I'm not naming all of them. And this is great. And you find a bunch of CVs in the field and a bunch of Dwarf novae in the field. But what I'm interested in is looking for cataclysmic variable CVs in globular clusters. So this is a picture of a globular cluster. This is 47 TOC, and you see that you can imagine that the challenge is a bit different because this is really a mess. There's a lot of stars in this, and there's really a lot of reasons why we want to study this. So I don't have to convince you, but I mean, really understanding the binary population of a globular cluster is very important because these binaries are the driver of the dynamical evolution of the globular cluster, particularly the black holes, but also understanding the population of CVs, the binary evolution models, if they actually work and if they actually predict what we're seeing, is very important to understanding globular cluster. In the context of cataclysmic variables, there's a large predicted, so I'm emphasizing this again, predicted population large at a known distance in globular clusters. And they're potentially very different from the field. You have a new way of making CVs. Dynamical formation of the system is unavoidable. You will destroy some of the systems that you would have formed in the field, and you would have formed new systems in globular clusters that you wouldn't have formed in the field because of this dynamical really environment where you have all this interaction among all of these stars. And there's a lot of open questions about CVs in globular clusters. Of course, I'm not going to be talking about today, but I'm really interested in starting thinking about all the white dwarf binaries in globular clusters and what that tells us about probable sources and population in LISA, which is going to be in the future. So how can we look for CVs in globular cluster? We can play the same game. Let's look at the Dwarf nova. If they're the majority, maybe we can get all those Dwarf novae in globular cluster. People have done that. It has not been the most successful endeavor. So we have only 17 confirmed Dwarf novae in a few globular clusters. There's 150 globular clusters, and people have been really doing this with Swift. This is an example, also with HST. And there's really evidence in the sense that Dwarf novae are probably very rare in globular clusters. And people have tried to explain this with some theories that we should try to test and see if this is what's going on. So like I told you, there's probably some magnetic CVs that they don't show these Dwarf novae. So are they all magnetic for some reason? Are they the CVs that exist in globular cluster? So we should be looking at that and see how we predict that. So the best way to find cataclysmic variables in globular cluster is, instead of looking at millions of stars, they are known X-ray sources, and they are known far UV sources. So let's look at the X-ray sources, and you see the same globular cluster, NGC 6397, HST optical. Near UV, it gets much easier to deal with. And then you look at Chandra, and now you only have dozens of sources, depending on the globular cluster, to look at. And this is what people have been doing in the past to find cataclysmic variables in globular cluster. So this is a color magnitude diagram. Each point is an X-ray source from Gaia with the probable optical counterpart. And I stress that each one is an X-ray source, and then you put them in the beautiful color magnitude diagram. If they are in the region where CVs are, and particularly if they show excess of H alpha, that's a very good candidate for a cataclysmic variable in globular cluster. So you see this kind of population of CVs in this cluster. This is 47 TOC. This one has a bunch. This is the really very well-studied globular cluster. This is work by Liana Rivera Sandoval, 47 TOC. And hopefully you'll notice, and I will show you again, that the population is different. You have this core collapse to the right, and non-core collapsed globular cluster to the left. And the population seems to be, and this is low statistics, there's a few globular clusters that have been well studied to find the CVs in the X-ray. And you see this bimodal population to the right, and this continuous population to the left. And we need to try to explain this. And this is really true, that you have this bright CV population near the core of the globular cluster, and this fainter, maybe older population outside of the center of the globular cluster versus this continuum population of CVs. So what are the simulation telling us? There's some really nice work by Belloni et al. About predicting number of cataclysmic variables in globular cluster, and is that many of them are X-ray faint. Many of them are old. That's why they don't go into outbursts that often. There are no outbursts. So maybe that's why we can explain that there's not that many that are no outbursts. There's a population beyond the half-light radius, a population outside of the core. So the point of this is that the models are telling us there's a predicted hidden population of cataclysmic variables in globular cluster that we are not looking at because our sample is biased and the way that we have been looking for these CVs. So of course, it works in the same, we have a sample, but it's a biased sample. Particularly, it's biased in the X-ray because we are only looking at that bright 10 to the 29, and this is really depending on the globular cluster, X-ray bright CVs in globular cluster. So as a summary, few CVs per cluster, few clusters very well studied, with a bias in the X-ray. We're only looking at those bright X-ray sources. We need to look at more type of different globular cluster, different metallicity, different dynamical state, core collapse versus not core collapse, because there's already some evidence that it matters where you're born in that sense. It matters if you're looking at a core collapse versus not core collapse for the population of cataclysmic variables in globular cluster. Something I didn't stress, but it's also very important. We don't know the period of this system. We don't know the orbital distribution. We only have really a handful of systems that we know the orbital period. So if we can get the orbital period, really get a nice orbital period distribution, compare it to the field, we can learn something about binary population, binary evolution in this dense star cluster, like globular, old star cluster, like globular cluster. So we need more detection, we need more periods, and of course, are they all magnetic or not? So this is where the SCOBA survey is going to do. So this is a survey using archival HST data, because there have been 30 years of data with HSTs, and some globular clusters have been observed quite a few times for other purposes. And we're going to look many different types of globular clusters, core collapse versus no core collapse, different metallicity. And we're going to look not only in the core, which people have been looked before, but also in the outskirts to see if that population beyond the half-life radius actually exists, and if it's there part of the globular cluster. So we picked 7 globular clusters with good archival data, meaning a lot of exposure times, a lot of epochs, so that we can see variability. These systems are very variable, not only in the outburst. You have this accretion disk, so you have this flickering, and maybe we have the variability and the colors, where they are in the color magnitude diagram, we can get new candidates that are not X-ray bright. So I'm going to show you some results of preliminary results of NGC 6397. It's a very interesting globular cluster, the closest core collapse, only 2.4 kiloparsecs away. There's some CV candidates, and I state that they are candidates because they have not been confirmed. We really don't have spectra with many of them. This might change soon when we get there's some new spectra. We can start really confirming them. And there's 2 pulsars. So there's all sorts of interesting stuff in globular cluster. This is how the HST data looks like. It was taken back in 2005. There's 126 orbits. So there's 126 epochs for each of these systems. We're looking at the blue end. Going to spoil you the answer. We have not found them. I'm still working on this data, but we have not found any new X-ray faint cataclysmic variables. I have to really think, if you have an idea how much this survey limits, if we have found them or not, if they are there, we are not sensible enough. So this is an interesting question. Where are they? We haven't found them. Stay in touch. But of course, there's a lot of interesting stuff in globular clusters. These are factories of binaries and X-ray binaries in general. So there's a lot of interesting stuff that we have the light curves of. So we should look at them and see what the optical light curve, blue light curve tells us. And in particular, I'm going to be talking about the first result we got from the surveys. It was not about CVs, but it was about a redback spider pulsar. So these are very interesting objects. Globular clusters have a lot of them. They produce many pulsars. And you have a pulsar, and then you have a star close to filling its rho lobe, maybe main sequence, and it's being really destroyed by the pulsar wind, by all the pulsar radiation. So then you have this dust of ionized gas around it that actually you see them in the eclipse in the radio. So these are called redbacks because this is kind of like a black widow, but it's a spider in Australia. So there's 2 types of spiders, pulsars in astronomy. Maybe a third one is a huntsman, another type of spider. But yes, you have this dust that actually obscure the radio. You have eclipses in the radio, and we think it's this neutron star really destroying its companion. So it was part of our data set, X-ray, steep radius source. This is the position of CMD. This is how it looks in our HST data. It's very variable. So of course, we tried to find a period, and we were able to find an orbital period of 1.96 days. And we were able to find it even if it was missing radio sources. Doing radio timing of in globular clusters is hard. It's very hard because you have to account for the acceleration. And now if you have this eclipsing system, that also messes up your data. So maybe they didn't take data in the phase that they require. So if this optical can help you constrain the parameter space that you have to look at, that could help potential follow-up radio timing finding of these pulsars in globular clusters and really get a nice real sample of these systems that they exist in globular cluster. So it was finally confirmed after we published the paper with radio that they actually went and looked. I'm not sure if they got new data, but I should have checked. But the orbital period, indeed, we were able to find it, even if was missed and later confirmed in radio. So what we did, we found, remember what we wanted to do, even if we didn't find any cataclysmic variables, we found some, what I'm going to call blue variables, which are variables that are in this part of the color magnitude diagram, in this part, far from the main sequence in H alpha minus R, and far from the main sequence, far from the, or near the wider sequence in this color, and we have Likers. So we're going to do periodicity search. So we did that. We did a periodicity search in all of our Likers, and these were some candidates that stood up that are in the right part of the color magnitude diagram and show some sort of periodicity. We just did very basic false alarm probability, but we should do some more interesting things to find other interesting stuff in the globular cluster. So I'm not going to talk about all of them. Some of them are known CVs. I'm going to show you the Likers. And the particular one that we found and just published this year, it was what we think it is a helium core white dwarf candidate in NGC 6397. So we were very excited because this is a position in the color magnitude diagram. It's variable. I'm going to show you the Likers. So, okay, we found one of the CVs. Let's keep doing it. Let's keep looking. But no, if you look at the H alpha minus R, it doesn't show any evidence of excesses in H alpha. So we don't think this is an accreting source. This is the position in the color magnitude diagram. We put these the tracks of the helium core white dwarf. These are very interesting objects. These are binary evolution. These are product of binary evolution. These are basically the core, the strip core of a star. There's a lot of them. They're called, especially in this mass range, extremely low mass white dwarf, and they wouldn't have formed unless you have some binary evolution. So it's very interesting to try to find them in globular cluster and actually confirm them as such and confirm them as binary, because many of them are binary in the field, but we don't really have, people have tried to find their binarity in globular clusters, but in a different way than we're going to try to do it with spectra. So we think what we're seeing is a 0.16 solar mass white dwarf, so extremely low mass white dwarf, product of binary evolution, and you see 6397, but there's a periodicity. So we really try to explain this 18-point-hour periodicity that we see in the Likers. The other hint that we have for these systems is we have some really low resolution spectra, really not low resolution, but really low signal to noise. It's 25-second exposure time. This was not for this. This spectra was taken by the Muse team. They're doing great work in globular cluster. But you definitely see, thankfully, these Balmer lines, and what we see is the fit to the H alpha and H beta, and you see that it's redshifted. So by different amounts, so that will be important in the future. So we think this is a binary candidate for sure. This is a binary helium core white dwarf. So still, what is the explanation of the periodicity? So we went through all the kind of try to explain it. We couldn't explain it as orbital period. So what we think we're seeing is evidence of rotation of this white dwarf. So we're seeing a white dwarf rotating with a periodicity of 18.4 hours. How can we explain that we're seeing this modulation in the Likers? What we think we're seeing is magnetism. So we're seeing evidence of magnetic helium core white dwarf in NGC 6397. Of course, this is a testable hypothesis, and what we want is new spectra, better spectra, to try to fit the profile of the lines to actually confirm the mass and the surface gravity, and follow up photometry or spectroscopy to actually confirm the orbital period, and this is not the orbital period. There's some hint of magnetism also, because maybe what we're seeing in the difference between the red shift and the blue shift in the H alpha and H beta, maybe it's due to the quadratic Zeeman effect. Again, testable hypothesis, we should be able to see evidence of magnetism in new spectra. So that's what we want, and this is what we're claiming we're seeing in there. So I'm not going to go through the rest of the systems. Again, we have some also Likers of known CVs. It's important to try to categorize in what type of CVs. This is the first time we're building the catalog of what is actually the type of CV we're seeing in globular clusters, and the Likers can help us in that. Some other interesting variables, maybe this is a pre-cataclysmic variable, meaning just a detach. There should be a lot of them, but it has been hard to find them. So if we can find them this way, CMD, variability, the orbital period, that could be very interesting and important to try to constrain those binary population models and we predict how many of them there are, what is the orbital period, and how rare is to find them. So to kind of finish with NGC 6397, Where are all the CVs? I don't know, but still this variability searches works. We find a lot of interesting binaries, in particular wide dwarf binaries that should be in global clusters and haven't been found before. And we will keep searching for variables and those CVs. I'm not going to show you data for M92 for sake of time, but we also have some really nice variables in the core. So you see people have done this work in the past, of course, especially M92. But really HST can look in the core. This one also has a bunch of HST archival data. So you have some really beautiful binaries, really beautiful variables, sorry, that you can see with HST. So maybe we can study the blue star population in the core and what the radial distribution tell us about this type of systems, and because they are also product of binary evolution. So work in progress. Stay tuned for M92. I mean, M92 is a very interesting cluster. There's some steep radio sources that I'm interested to follow up. So if you're interested in Pulsar and how to tie these pulsars, not only via timing, because you can miss them in timing, but via X-ray, radio, and optical light curve, which talk. And what I want to leave you is with, I'm also interested in other stuff, and there's people in this institute that work with TESS, for example. I'm interested in how can we, I only study the known population of AM CVn, but we should be able to detect them in TESS. So how are you doing if you're working with some transients? How are you doing that with TESS? I'm very interested to talk about finding them actually in the TESS data set, new AM CVns via their periodicity, via the super outburst, the duration of those super outbursts, so the duration of those outburst events in TESS. How are you dealing with crowding with TESS? Crowding, it's a big problem with TESS. I'm very interested in how you're doing that. And my interest in symbiotics. So these are red giant with a white dwarf, and those Lycors are kind of crazy, but there's some periodicity that we see in them. How can we explain that? So very interested in looking at the periodicity in these red giant stars, particularly these symbiotics, and see this periodicity. Some people say that we're seeing some evidence of magnetism of these white dwarfs, and can we follow them up with TESS? So that's what we're trying to do. So a lot of people work in galactic dynamics here. I'm very interested in what the binary population of these CVs tell us about binary population, binary models. We have some really nice candidates now with Gaia and some surveys of really halo CVs that we want to go after and actually get them as really halo CVs. And how are you guys all, the people working in here, working with halo CVs, like halo versus thick disks? So I'm very interested also to talk about that. So that's all I have for you today. Thank you for coming, and I'm very happy to answer any questions you will have.
All right, we do have time for questions, either in the room or online. I wanted to ask one thing about with your looking for CVs in globular clusters. So how big of a sample would you need to really be saying something useful about binary evolution in clusters compared to the field?
I mean, because we haven't found any.
Right.
And we really we're thinking what we can constrain with the data set we have, if we were sensitive enough for those or not. So that is something I'm thinking about, but I don't have the answer. But I think even getting a few of them will be important to say, yeah, they are indeed there. And what I'm predicting maybe, and where they are in the color magnitude diagram. Are we going to find those? We're probably going to find those old ones. Are they there? And how many they are? So how many of these old period bouncer of 80 minutes or something, they are there? And then look back, do we see an outburst or not? And then get that. So I don't know. That's a good question and something I'm thinking about. And of course, if you have any, more than happy to talk about possibilities and how to really constrain this. But first we have to find them or not find them, because they're predicted. Even in the field, there's problem finding them. There should be a lot of period bouncer. What are they? I don't know. So there's some problem for sure. And there's extra problem global cluster because the crowding.
Any other questions? Yeah.
So yeah, regarding finding these in the GCs, like right, so like there's tons of strange binary products in there. So like, you know, you might think that they should be in there, but are there other effects also like in terms of like disrupting the binaries, mergers, enhancement of the social effects that might explain and suppress the population that you're now finding in the secreting state? Like, is there, you know, could that actually be like that? Right. I mean, it might not be too surprising that you're not finding any in that state. If you're disrupting a bunch of these binaries.
But you're also creating some of them. So for example, these CVs that are very bright, what people think in the models, where are the NGC 6397? This is how they're explaining this bimodal population. These are near the core, and these are actually dynamically formed CVs versus these old CVs. So you are creating some news, but you're also destroying some, that is right. But and this is not tested, and that's why we're doing it. There's still, the prediction is like there should be more. It's true, we haven't been sensitive. So it's not weird that we haven't found them yet, but I will argue that it is weird if we don't find them, because our sample is biased in the X-ray. So many of these will be low accretor, do not show in our X-ray searches. So it's not surprising. They try to explain our current sample, fine, because, you know, of course, you have to explain what you have. But now we should get new sample and see, do the models still work? Because I think if we don't find anything, it will be surprising. And of course, I'm not a modelist, I'm an observer, but I love working with modelists and really, you know, prove them right or prove them wrong. It's always fun.
Any last questions? Great, if not, let's thank Manuel again. And there are still plenty of times available to meet with Manuel this afternoon if anybody wants to talk with him further. Link was in the email, so feel free to sign up.